In this video, we're going to look at a theorem that we're probably all pretty familiar with. It's called the fundamental theorem of arithmetic. It's also known as the unique factorization theorem, and it was proven by Gauss in 1801, but something similar exists in Euclid's volumes called the Elements. And FTA is the fundamental theorem of arithmetic, and what it says is that if n is a natural number that it's at least 2, then either n is prime or n can be expressed as the product of primes in a unique way. Now, here's a couple of simple examples. 17 is a prime number. So how do we write it? As a product of primes, essentially it's just a prime. That's the case where n is prime, so you write it just as it is. Now, 72 is not a prime number. It's equal to 2 to the third times 3 squared. That's 8 times 9. But this is the prime factorization, and we generally write the prime factorizations in increasing order. So we'll write 2 to its exponent before we write 3 to its exponent. And the number 360, as an example, would be 2 to the third times 3 squared times 5. That's its prime factorization. Well, let's prove this, and it's really going to take two things. First is we're going to have to take a number n and show that it can be written as a product of primes. Then secondly, we will show that it can be done in only one way, a unique way. Okay, so let's begin our proof. If n is a prime number, then we're already done. It would be like this case. We're done. There's nothing else you need to do. 17 is a prime number, for example. Okay, otherwise, n is composite, which means it's not prime. So let's let n1 equal p1 times n. I'm sorry, I said that incorrectly. Let's let this number n equal n1, or p1 times n1. Let me do it in the order I wanted to do it. So since n is composite, we can factor a prime number out of it. So we're going to call n p1 times n1. So p1 is prime, and obviously n1 is going to be less than n. So I will say that n1 is less than n. Okay? And n1 is obviously not a 1, because otherwise n would be prime. N would equal p1. All right, so then, let's ask ourselves this question. Now let's take a look at n1. If n1 is prime, well, then we're done. We're done because n would equal p1 times n1, a product of two primes. So assume that n1 is composite. All right, so we're assuming n1 is composite. Then we could say, let's let n1 equal p2 times n2, where p2 is prime. And 1 is less than n2, which is less than n1. All right, well, if n2 is prime, then we're done. We could say that n, which is p1 n1, n1 is p2 n2, and those are both prime. We could say n is p1, p2, n2, and we'd be done. So we're just going to continue that process. I'm going to say continue this. This may not be a rigorous proof, but you'll get the idea of how the proof goes. All right, so continuing this. We'll notice that every time we do this, if I were to create a, let n2 equal p3, n3, and so on, n, n1, n2, they're always getting smaller. n1 is smaller than n. n2 is smaller than n1. Since we're talking about positive integers, and a finite number of them, since this set is finite, in other words, eventually this process will terminate. Eventually, and n equals p1, p2, all the way up to, we'll call the last one pk. N is equal to the product of all of the primes that we obtain, where p1, p2, all the way up to pk are primes. All right, well, that basically proves the existence of a prime factorization of every natural number n, every natural number greater than 1. Okay, so maybe I'll write that as this portion is the existence. So we've proven the theorem. If we removed this, we have proven the theorem. Now we need to show that it can be done in a unique way. So, for that portion, let's say to the contrary, suppose, this will be like a proof by contradiction. To the contrary, actually, will this be a proof by contradiction? I don't think it will be. I'm going to erase that. Let's just suppose that, there are two representations of n. Now what I mean that is that two different products of primes, two different factorizations of n factored into the prime numbers. Okay, if that's the case, if there are two of them, we can say let n equal p1, p2, all the way up to pr, I'll say. So r prime numbers multiplied together that give you n. And we're going to say that's equal to q1, q2, all the way up to q, and I'll say q sub s. And we will assume that r is less than or equal to s. Since one of them has to be less than or equal to the other, we'll just assume that r is at most s. And of course, all of the pi's and qj's, I'll call them, are primes, or prime. So we're assuming that this is one representation of primes, and this is the second representation of primes. We need to show that they're equal, that it's impossible for them to be different from each other. And we will assume that we've written them in the order that we prefer, that P1 is less than or equal to P2, less than or equal to, all the way up to PR, and that Q1 is less than or equal to Q2, less than or equal to, all the way up to QS, so they're a non-decreasing sequence of primes being multiplied together. Okay, well, what does that tell us? Because we've established these two representations, I know that P1, this prime number, it certainly divides in, of course, all of these numbers divide in, but n can be written as Q1 through QS multiplied together. So P1 divides Q1, Q2 to QS. That's the product of all of the Q's. Well, that implies that P1 divides one of these Q's because these are prime numbers. If P1 goes into a collection of prime numbers multiplied together, P1 has to divide one of them. So I'm going to say that P1 divides QK for some K. And what does K go from? For Q, it's going to be 1 to S. So 1 to S. So P1 divides, goes evenly into QK. Well, since these are prime numbers, that means that P1 is equal to QK. All right, because we're only dealing with prime numbers. The only factor of QK is 1 and QK itself. So if P1 divides it, we know P1 isn't 1, so it must be QK. But that tells us that since these are written in increasing order, that for sure tells us since P1 is equal to one of these, that tells us that P1 is greater than or equal to Q1. Okay? So we know that P1 is greater than or equal to Q1. So now let's look at it from the other side. Q1 must divide in. So I'm going to do basically the same thing. Q1 divides P1, P2 times all the way up to P, let's see, P goes to R. And that means that Q1 divides PM for some M in the set, the P's go from 1 to R. 1, 2 to R. Excuse me. Well, you can probably figure where I'm going from here. That means Q1 is equal to PM, which implies that Q1 is greater than or equal to the first, P1. Because remember, these P's are written in increasing order, or non-decreasing order, I should say. But what does this tell you with these two things that I put in boxes? P1 is greater than or equal to Q1, but Q1 is greater than or equal to P1. We have only one option. Thus, P1 equals Q1. Now, I'm running out of room. I would then repeat that with Q2 and P2. And we would determine that P2 must equal, Q2 must equal P2. Q3 must equal P3, and so on. So I'm just going to conclude it by saying, therefore, Pi is equal to Qi for all I in. And how far do I have to go? 1, 2, all the way up to R. Or I could have used S, because S and R are equal to each other. Because Q1 and P1 are equal, Q2 and P2 are equal, all the way to the end of the list. And that's the end of the non-rigorous proof, I'll call it. So this second half of the proof showed the uniqueness. So the first half showed that every number could be written as a product of primes, and the second half showed that that prime factorization of the number is unique.